Good morning, everybody, and thanks for joining. My name is Jase Bernhardt. I'm an assistant professor in the Department of Geology, Environment, and Sustainability at Hofstra University, and I'm really the university's point person for studying and communicating and researching and teaching about meteorology and climate change. And today we're going to focus on meteorology, and we'll be talking about extreme weather on Long Island. So today we are going to talk about the following topics. We'll briefly touch on some of the recent extreme weather we've seen. You all probably noticed there are some interesting weather conditions yesterday across Long Island in the Northeast and other parts of the country before that. So we'll break that down a little bit. And then we'll get into just a few types of hazards, weather hazards that are most impactful on Long Island. East Coast winter storms, thunderstorms, tropical cyclones, and then we'll finish up just talking a bit about the weather forecast, just a few words on what the short and slightly longer term weather outlooks might look like. So throughout this talk, feel free to send a chat if you have any questions. Those are being monitored and can be conveyed to me. And then at the end, we'll have plenty of time for questions. And at that point, you can come off and unmute yourselves and ask any questions. Any discussion would be great. But before we get into the material right now, what I wanted to do was just come away from the presentation briefly and initiate a Zoom poll. So a poll over this Zoom software means that I'll start a poll, a box will pop up, you can vote for your choice, and then after that, you'll be done voting, and then it'll close soon after that. So I'm gonna go back into the software here. So again, I'm gonna start up a poll. Not obligatory to vote, but I'd love to get some feedback, and we can then sort of discuss the results at the end of the presentation. All right, so you should all now see a box pop up. So the question is, which type of extreme weather seems most impactful in your experience living and growing up or whatever on Long Island? So we have 3 different options here, and then just a something else if maybe you think there's another option that's most impactful. So I'll leave this open for about 60 to 90 seconds or so. So again, a box should be popping up around your screen. If you're on a phone, unfortunately, it might be a bit trickier, but it should be initiated up there. If not, it's no problem. You can also feel free to put your vote in the chat. The options are winter storms, hurricanes, or thunderstorms, or just something else. So if for whatever reason the vote box didn't pop up or you just joined in, feel free to send a chat through for your vote. Again, the question is, which type of extreme weather seems most impactful for Long Island? And the options are winter storms, hurricanes, thunderstorms, or something else. Leave this open for a few more seconds. And it's actually a very close vote here. So again, any voting can help decide at this point. All right, so let's leave it open another few seconds. And again, I'll repeat the question one more time. If for some reason it didn't pop up or you just joined in, you can type in chat your response. Which type of extreme weather seems most impactful for Long Island? Winter storms, hurricanes, thunderstorms, or something else? All right, 10 more seconds, then we'll close the poll. All right, so I'm going to share the results, but for some reason that does not pop up. We actually had one type in vote for hurricanes. So that means hurricanes is actually the narrow winner. Hurricanes wins by 1. So hurricanes are seen as the most impactful type of extreme weather on Long Island, followed closely by winter storms, just one behind. Then it looks like we had 2 people vote for thunderstorms, and then 1 said something else. Whoever said something else, if you'd like to type that in the chat box for everyone to see, if you feel comfortable, That would certainly be interesting, but no pressure if not. So unsurprisingly to me, winter storms and hurricanes are seen as two of the most impactful types of weather on Long Island, and I would definitely agree with that assessment. Winter storms, for the fact that there's a lot of them, even though every one might not be super impactful, there's a lot of them, and sometimes they can be. And hurricanes, as you probably know, are less common on Long Island. But on the other hand, when they do impact Long Island, they can lead to very extreme results. So we're going to talk about all three of these topics today: winter storms, hurricanes, and thunderstorms. All right, so thank you everyone for participating. All right, so we're going to go back into our presentation now and get going on some material. So we just had our Zoom poll. Again, we found that by a nose, we had winter storms and hurricanes really battling it out for which was the most impactful weather on Long Island, and by a nose, hurricanes won just by one vote though over winter storms. Thunderstorms a distant third, and there's one vote for something else. So we're going to talk about all three of these weather phenomena which impact Long Island and learn a bit more about them here today in our presentation. And again, for those of us who just joined, feel free to chat in a question at any point. I'll check that periodically and get to those. And then at the end of the presentation, we'll have plenty of time for questions and discussion about anything that you see. And also my contact info at the end of the presentation if you want to reach out via email or social media to chat more as well. That would be great. All right, so first wanted to just do a quick bit about what has been happening in the weather. Weather has actually broken into the headlines a bit the last couple of days. And for a little far from home, the reason weather was in the headlines was because on Sunday, April 12th, there was a major tornado outbreak across the southeastern portion of the US. And this is a really severe outbreak and a pretty wide-reaching geographically. There were tornadoes reported from Texas all the way to North Carolina. So we had tornadoes reported in several different states. And right in the middle of that swath there, Mississippi, Alabama seemed to get the worst of it. And we actually had a tornado. One of the tornadoes was exceptionally strong. A few of them were exceptionally strong. And one of them, the picture in the background you see here, is actually strong enough, sort of hard for us to imagine, especially being on Long Island where we rarely get tornadoes. This house is, you know, not huge, but not tiny either. This entire house was picked up off its foundation by the tornado and dropped on the other side of the road. So just imagine how powerful this storm must have been to pick up an entire house like that and move it somewhere else. So sadly, there are several fatalities from these tornadoes. Fortunately, there was lots of warning in advance of these storms, so it could have been a lot worse. But even with warnings, that can save lives, but we can't do much about the damage. So there was, of course, significant damage across this large swath of the southeast US. With several tornadoes, dozens of tornadoes, mainly on Sunday into Sunday night across the southeast US. And then closer to home, you all surely experienced the strong winds yesterday on Long Island. This is from the same storm system, a big low pressure system, a cyclone, a storm, formed in the central part of the US and strengthened as it moved up through the Midwest, Great Lakes, and up into Canada. And that essentially dragged through what's called a cold front. So that explains the colder air today. But in transitioning from the warmer air earlier yesterday to the cold air today, we had a clashing of air masses, which helped bring about some thunderstorms and, of course, heavy wind, very strong winds. Top wind gust at sort of one of our reliable weather stations was 61-mile-per-hour winds gusting at Islip Airport yesterday. So wind gusts of 60+ miles per hour over Long Island. There were scattered power outages. Feel free to chat in the chat box if you wish to mention if maybe you were impacted by the power outages and how long that may have affected you. So scattered power outages across Long Island and other parts of the Northeast and New England, again, mainly due to those very strong winds. And we have a fun little clip here of a weather station in New York State. And the wind was so strong, it was blowing around this portable toilet. And then you even see a roll of toilet paper in the wild here that must have gotten somehow blown out of the porta potty into the field here. So we see that valuable toilet paper was even being blown around by the wind. All right, so now let's start talking about each of our three types of hazardous weather that impacts Long Island. And the way we'll do this is I'll present some slides on each one of these topics. We'll keep it pretty basic and just have a few more advanced things on each one. And at the end of talking about each hazard, I'll just quickly check the chat box, see if there's any questions, things to maybe talk about a bit more. So feel free at any point to type into the chat box if you have a question. And in due time, I'm happy to get to it and further expound. And also, as I've mentioned, at the very end of the talk, there'll be plenty of time to unmute and have any questions or discussions that come up. So first, we're going to be talking about our East Coast winter storms here. So what is an East Coast winter storm, or ECWS is the abbreviation that we often use here. So there's lots of different names for these storms. So you maybe have heard it referred to as a blizzard or a nor'easter or a coastal storm or just a snowstorm or a winter storm, something like that. And unlike something like a hurricane, as we'll get to, there's not really a set criteria or definition for it. So East Coast winter storms is the preferred term that I have and some scientists and researchers use. But again, lots of names out there. It's the same general thing. And as you might imagine, the name tells you a lot about them. They form in and around the east coast of the US, often just off the coast over the ocean, and mainly occur during winter. And they're low pressure cyclones or storms. So hence the terminology East Coast winter storm. So these occur during the cool season, not exclusively in winter. They can actually occur starting in the fall, sometimes October, and then even early April sometimes there can still be these types of storms, but they are most frequent during the winter months, so think December through March. The key feature is this is a low pressure system. So on a weather map, maybe you've seen the red L before and the blue H, and the red L refers to low pressure, the blue H refers to high pressure. Typically high pressure is boring weather, clear and calm, not much precipitation, usually not any. So we don't talk about that much because it's not very exciting. Conversely, that red L that you see is a low pressure, that's a storm. A so-called closed low pressure system, as you see on the bottom right image here, just means that's a very defined circulation, a very defined storm. So these low pressure systems can occur all over the world. Hurricanes are an example of a low pressure cyclone, for example. But when they form, again, off the east coast of the US, so often over the Atlantic Ocean during the cool season, they're typically East Coast winter storms. They generally move to the northeast, and this little animation loop here is an example of an East Coast winter storm. This is from early January 2018. A little over 2 years ago. This is a storm that brought lots of snow and some wind to New York City and Long Island. Actually led to lots of travel delays both during and then after the storm at the local airports. So notice how it looks like a storm, right? You see this little swirl, so that's the low pressure center right there. And this is just the weather map depiction of it below that. And notice how it's moving. It's sort of going up and to the right. So it's moving to the northeast. And if you can sort of picture the circulation, notice how there's sort of a swirl around it. And that swirl dictates that the winds are northeast, out of the northeast for the East Coast, for New York City, Long Island, New England. So that's where these storms get their name from. Sometimes people call them a nor'easter. And that has to do with the winds coming from the northeast. So nor'easter, another name because of those northeasterly winds. And these storms often also move towards the north and east, up the coastline, essentially. And they can bring strong winds, heavy precipitation, and coastal flooding. So heavy precipitation, sometimes it's snow, but as we know, not always. Sometimes you just get a heavy rainstorm in the winter, especially parts of eastern Long Island. So it's not necessarily snow, but the precipitation is often heavy. And if it's cold enough, then yes, you do end up seeing snow from it. And sometimes they can rapidly strengthen. And this is actually a meteorology term called a bomb cyclone, or a meteorological bomb. And that was sort of an esoteric term for a while. But more recently, you might have started hearing that in the news or on social media. So that term's kind of been popularized recently. So a bomb just refers to a rapidly strengthening low pressure system. And this happens most frequently with these East Coast winter storms, often again, just off the East Coast. So sort of this loop here is sort of a textbook example of sort of when and where an East Coast winter storm would form. And one reason why they get so strong is the so-called clashing of air masses, which is a theme we'll see throughout today because this is a key ingredient for severe or extreme weather. And in this case, as it turns out, we have a warm ocean current known as the Gulf Stream, that fairly warm ocean water off the east coast of the US. And even during the winter, that's relatively mild for this latitude. And that clashes with very cold air that can build up over parts of Canada and then come down to the south and end up over the northeast US. So the very cold air from Canada can sometimes clash with the warmer, moister air over the Gulf Stream of the Western Atlantic, and that can help to spin up and then rapidly strengthen these storms. So that's sort of a quick reason why we see these storms frequently off the east coast of the US. It has to do with the physical geography, the cold air that can build up over Canada and sometimes come down towards us, and then the warm Gulf Stream oceanic current over the Western Atlantic. So what are the impacts? So as I mentioned, heavy precipitation. There could be freshwater flooding, so that means that any inland bodies of water, like lakes or rivers or streams that aren't related to the ocean. I know there's not that many of those on Long Island, since most everything runs into the ocean or is sourced from the ocean. But especially when there's rain from these, that can lead to freshwater flooding, especially if you go a little bit further inland, away from the coast. Wind can be significant. And of course, a big impact on Long Island is coastal flooding and beach erosion. And believe it or not, that can often be very significant from these storms. These storms are strong enough to push in sometimes a few, and in rare cases, to several feet of water, of surge, extra water essentially from the ocean towards the coastline. And then that can lead to erosion of the sand and beaches along the coastline, and sometimes push further inland, causing flooding along the coast and even a little bit inland. And it's important to quickly familiarize ourselves with the lexicon here. The New York National Weather Service Office is going to issue weather warnings, watches, and advisories for each aspect of the storm here. And those are being communicated online through social media, by a broadcast television, if it's very extreme, by direct text message to your phone sometimes, and also on those flashing highway signs. Those warnings, watches, and advisories are issued by the New York Weather Service Office, which is actually located out in Suffolk County, out in Brookhaven National Lab, which is in Upton, New York. And these are some examples of the types of warnings you might see from the National Weather Service Office as they relate to an East Coast winter storm. If it looks like there's going to be some extreme wintry conditions coming up in the next 48 hours, but the exact details are still a bit uncertain, winter storm watch will be put up. And that's sort of your first clue to get prepared and know that there might be something big coming. Then once it's pretty certain, usually within 24 hours of the start of the storm, a winter storm warning is issued. And a winter storm warning for Long Island is generally issued if it looks like there'll be at least 6 inches of snow, or if there's going to be significant impacts from other types of winter precipitation. So let's say there's going to be a lot of ice combined with snow, or sleet and snow, even if it's a little bit less than 6 inches of snow. If there's also going to be sleet and ice on top of that, that can also trigger a winter storm warning, but generally 6 inches of snow or more for our winter storm warning. If there's still going to be some snow, but not quite as extreme, a winter weather advisory can be issued. That's going to be for at least 3 inches of snow. Or again, if there's going to be a combination of some snow and some sleet and some ice. And then last but not least, we have our blizzard warning. And that's only if very certain criteria are met. So you actually only officially have a blizzard if you have strong winds and reduced visibility from either falling or blowing snow. So you actually don't need snow to be falling from the sky to create a blizzard. You could just have snow blowing around, blotting out the visibility. That's pretty uncommon on Long Island. Generally, our blizzards come during sort of the heat of the storm, when there's a very strong storm, not too far away, but cold enough for snow. And then we have heavy snow. And then, as you might have experienced before, the stronger the wind, the lower the visibility is. So once you have winds of about 35 miles per hour and moderate or heavy snow, that can make the visibility a quarter mile or less. That means if you look out, you can only see a quarter of a mile. Sometimes only an eighth of a mile or even less. Sometimes it might only be several hundred feet they can see. And you can imagine how difficult travel can be. It's basically impossible during a blizzard warning because you can barely see a car or two in front of you. And of course, planes cannot at all take off because the visibility is so low. So blizzards can be extreme and impactful, but I do want to really highlight this coastal flooding threat because along Long Island, that's often the biggest impact we see from East Coast winter storms. So what can happen here is that, again, the strong storm can push water in to the coastline and then even into bays and inlets along Long Island. We have lots of those, of course. And then you can get coastal flooding. And timing of the storm can be important as well. And it's just sort of luck. So if the storm sort of passes by Long Island right around high tide, that can make the storm surge even worse. And as we know, there's regular tidal cycles, and if the storm moves slowly, you can actually sometimes see that the storm surge is occurring over 2 or even 3 tidal cycles in the case of a slow-moving storm. And that can really lead to issues. Imagine if there's multiple tidal cycles in a row of storm surge flooding coming in. Definitely by that second high tide, you're seeing the water very easily inundating inland and leading to issues. And also the beaches really getting eroded with the sand getting carried away from it. So these East Coast winter storms, which there can be multiple per year, always take a toll on the beaches and the immediate coastline. But how extreme those impacts are can be dictated by the speed of the storm. Again, slower moving can often be worse because it can impact over multiple tidal cycles, multiple high tides. The intensity, generally a stronger storm can bring more surge, but also the track. If the storm tracks in a certain angle, that can really maximize the amount of water that can be pushed in to, say, the south shore of Long Island, or other ways the north shore can actually get worse impacts sort of back on the other side of the storm from the Long Island Sound. All right, so what I wanted to do then is to sort of prove this impact of coastal storms is here's a table that shows the highest storm surges ever on Montauk Point, so on the east end of Long Island. And you might notice a few famous storms here. The year, month, and day of the storms is posted here. And this is telling you the left is the meters above sort of the average water level, and the right, the blue, is the feet above water level. So for example, this top storm here, that's saying we had nearly 8.5 feet of surge of water coming in at Montauk above the normal level. And of course, you can imagine what 8.5 feet of water coming into the coastline can do. It can be devastating. And that was actually, these top two here are actually from tropical systems. Just looking at the data can tell you that. Turns out 1954 was Hurricane Carol that impacted Long Island significantly at the end of August 54. And then 2012, I'm sure a lot of you know what that date was. That's, of course, Sandy. So 2 hurricanes are the top in terms of surge. So sort of gives us the point that hurricanes are rare but very extreme. But then the more common impact storms are actually East Coast winter storms. If we look at the next several cases here, we see wintertime storms. February of 78, some of you might remember the blizzard of 78. That's number 3 all time. Number 4 all time, October 1991, is actually the so-called perfect storm. There's a movie and book about that. That was sort of a hybrid hurricane / winter storm, but more towards a winter storm. And then the next several storms are all winter storms. So again, the point is most of the biggest impact events in terms of storm surge are actually coastal storms, East Coast winter storms, not hurricanes. but there are a few hurricanes on the list here, and those are generally most extreme. Another hurricane here a bit further down the list, this August 2011 storm, that's going to be Hurricane Irene. And then 1960, September, a bit further down, that's Hurricane Donna. So a few of these are hurricanes, but the vast majority of the top 20 are going to actually be East Coast winter storms. So actually most of our coastal flooding and beach erosion occurs during the winter from these East Coast winter storms. That's the real takeaway from this graphic here. And then just the last thing I wanted to mention regarding winter storms is something that's rare on Long Island, but can also be impactful, and that's called a snow squall. A snow squall is a sudden brief burst of heavy snow and whiteout conditions, so sort of like blizzard conditions in a way, but just occurring very suddenly, but for a short amount of time. Sometimes these squalls might only impact you for 5 or 10 minutes, but that 5 or 10 minutes can be very extreme. And the big problem is these can sometimes come suddenly with less warning, and they can lead to major traffic tie-ups because people haven't stopped traveling because it's clear out, but then all of a sudden the squall works in, and there can be some major problems. So here's a quick video I took from the roof of my academic building at Hofstra last year of a squall. So you'll see very, very intense. Yeah, I can barely see the buildings just feet away. I can barely see across the 2-lane street there. So again, squalls like this can set in very quick and it can be clear, and then 5 minutes later can look like that. And it's hard for people to quickly adapt to that. So you can often get major traffic jams, and unfortunately this occurred around in the afternoon when there's heavy traffic. So the National Weather Service actually just started rolling out recently here a new snow squall warning. And those can be pushed out when, again, it looks like there's going to be this very sudden burst of heavy snow. You typically only get an inch or two, sometimes even less accumulation of snow from these. But again, the very brief, intense nature of it can lead to issues. So if you ever see or hear about a snow squall warning for your area, definitely take note and try to stay off the roads. Oh, so that's it for the winter weather. So I'm gonna take a couple minutes now to field any questions in the chat box. So I'm gonna go out of the presentation here and back into the main session. Here's a few questions. The seasonality in East Coast winter storms, good question. That's going to have to do with the fact that you really need that air mass clashing, and the idea is that you want that extreme clashing. You want the really cold air mass contrasting with the warmer air mass. So the cold air masses really can't start to build up and come far south until October, even later, especially those midwinter months. So that's really going to help give us the opportunities for the coastal storms. So the winter time is best for that. The ocean water still stays fairly warm with the Gulf Stream even during the middle of the winter. So then the contrast with the very cold air masses coming down from the north and the Gulf Stream can help to spin up these storms. So, all right, that looks like the question so far. So let's hop back in towards talking about our next topic, which is going to be thunderstorms. So what are thunderstorms? So thunderstorms are actually constantly occurring in the Earth's atmosphere. And they're composed of tall, vertically rising clouds known as cumulonimbus. So maybe you've seen those tall, towering storm clouds that seem to keep building up and building up, especially on hot, humid days during the warm season. Those are cumulonimbus clouds, and eventually sometimes they lead to thunder and lightning and heavy rain and maybe some other impacts. And those are your thunderstorms. Thunderstorms are very important globally for redistributing heat and moisture across the world. So thunderstorms and really severe weather more broadly seems like a nuisance, and of course it is, but it's necessary for our Earth to sort of keep things in somewhat of a balance. It actually turns out the lower latitudes of the Earth have a surplus of heating each year, and the upper latitudes have a deficit of heating each year. So to balance that out and make sure the lower latitudes aren't warming out of control and the upper latitudes aren't cooling out of control, the Earth tries to get itself back into balance by transferring heat and moisture from the lower latitudes, closer to the equator and the tropics, up towards the higher latitudes. So as a result, that can lead to clashing of air masses, as I mentioned, and in general, extreme and sometimes severe weather. So we particularly concern ourselves with what's known as the severe types of thunderstorms. So the National Weather Service, as I mentioned, is going to be issuing warnings and advisories and watches for severe weather. And they have a set of criteria that triggers a watch or a warning for a severe thunderstorm. So thunderstorms can be strong. They can bring heavy rain and lightning and wind and even small hail, but not be considered severe. So you won't really get any warning about that necessarily. But if a thunderstorm reaches these certain criteria to be severe, then you will hear a warning for it. You might see a warning for it. You might see a crawl across the bottom of the TV screen. You might get a text to your phone. You might get you might see the flashing highway sign message. So similar to the winter storm information being disseminated. So according to the National Weather Service, a thunderstorm is severe if it contains wind gusts of at least 58 miles per hour. So basically winds as strong as yesterday's across Long Island at its peak. Those can be considered severe. Obviously, if there's a tornado, it's considered a severe thunderstorm, although you'd be preempting that with tornado warning. And if there's hail involved that's at least 1 inch in diameter, which is about the size of a US quarter, then you would be considered as having a severe thunderstorm. So how do we get severe thunderstorms? So you want a source of moisture or water that evaporates into so-called water vapor into the atmosphere. Sometimes that extremely moist air can be transported towards the Northeast from somewhere else. The Gulf of Mexico, for example, during the warm season can get very, very warm. It's almost like bath water sometimes. So that warm ocean water can help to fuel storms, and sometimes that very unstable air, so hot and humid air, 1 and 2 here, can get transported from the southeast US, from the Caribbean Sea, from the Gulf of Mexico up towards the east coast of the US into the Northeast. So when you get those hot and sticky days, as we've all experienced before in Long Island, that can sort of create our fuel for thunderstorms. Sometimes just that warm, humid, unstable air mass is enough to pop up some storms. Those are called air mass thunderstorms. But for Long Island to really get those very strong and severe thunderstorms, you typically need that clashing of air masses again. You need colder air to come in from the north and west to clash with the warm, moist air. And essentially what happens is the warm, moist air is lighter than the cold, heavy air. So the warmer and moister an air mass is, the lighter it is, less it weighs. And the colder and drier an air mass is, the heavier it is. So that heavier air can force that warm air to rise up. And air rising up is what creates clouds and storms. The atmosphere sort of telegraphs this for us. We see clouds, those thunderstorm clouds, often building up throughout the day. And that can lead to eventually storms actually occurring. That's sort of showing that warm, moist air is being forced to rise up as you go through the day. So you want often what's called a lifting mechanism to force air to rise up. So a front, which might be colder air mixing with warmer air. Maybe the surface heating differences. So one area is warmer, an area next to it is colder. Sometimes even terrain, mountains can help to fuel storms. Of course, we don't really have those to deal with on Long Island, but other parts of the world, that can be a trigger mechanism. So basically, you want the air to be able to rise up. Sometimes just having very hot and humid air is enough to get air to rise and storms to form. But sometimes you need an extra trigger, something else to force it to rise up. And as a quick example of air being warmer and rising up, this is known as convection. Think about the old adage, warm air rises. So higher floors of big buildings or apartments are often warmer. The warm air from lower down rises up. And if you think about cooking, you could say boiling water for pasta or whatever you want to put in boiling water. Think about you put your pot on the burner and you have the warmth coming from the burner. So the water on the lower part of the pot warms up first and then it starts bubbling and rising up. Same thing happens in the atmosphere of the Earth. You can actually almost think of the atmosphere of the Earth like a fluid. So the surface of the Earth is has the warmest air. so that warm air can start to rise up, especially if it's very warm and very humid. So that can give you your thunderstorms. And then finally, to get tornadoes out of thunderstorms, you want something called vertical wind shear. That just means that the wind speed and direction changes with height. And if you think about it, that can get your storm starting to rotate around. And so-called supercell thunderstorms can start rotating and sometimes pop out tornadoes. So that's not, vertical wind shear is not necessary just to get sort of your garden variety severe thunderstorms, but to get a tornadic storm, you need that spin to be around in the lower part of the atmosphere. And again, that involves wind speed and direction change with height. And you can sort of picture that as the wind direction changes with height, that can get your storm clouds spinning and possibly help a tornado form. There's other things that are needed for a tornado as well, but one basic requirement is going to be that so-called wind shear, getting that storm to spin around. And that, of course, was in place in the southeast US on Sunday especially, which unfortunately fostered the development of many tornadoes, some of them extremely powerful. Here's a brief look at the seasonality and climatology of severe thunderstorms around New York City and Long Island. I do apologize, these are not the best graphics visually, and they're only through 2006, and I wasn't able to easily find updated graphics, but that's fine. This is about a 27-year record through the 80s, 90s, and first part of the 2000s. So it actually gives us a pretty good idea of what things look like here. So a couple of graphics we'll go through quickly. So first on the left here, this shows the hourly distribution of severe weather. And it's sort of in this circled zone here on the map. So Long Island, New York City, most of Jersey, the eastern portion of Pennsylvania, up into the middle of New York, and then parts of southern New England. So this first graphic on the upper left here looks at the hourly distribution of severe weather reports. So again, this is either wind of at least 58 miles per hour, hail an inch in diameter, though they changed that criteria, it used to be just 3/4 of an inch, and then a tornado. And this graphic here shows the timing, the average timing of these storms, what percentage of the severe storms occur at certain hours. Note this is actually in the Greenwich Mean Time, so it's 4 hours ahead of our local time here. And meteorologists generally use this Greenwich Mean Time, this universal time. Otherwise, it get very confusing comparing one spot to another if they all have different times. So we just use a standard time to help with forecasting, especially across time zones. Anyways, this is telling us, for example, the peak here we see about 21 or 22 universal time, Greenwich Mean Time. That's going to equate to about 5, 6 o'clock p.m. Eastern time. So as you probably expect intuitively, the peak of severe thunderstorms across Long Island and surrounding areas is from the late afternoon through the evening. So the peak starts here, around 3, 4 o'clock, probably the max threat around 5, 6 o'clock on average, and still stays up there for a few hours towards 7, 8, 9 o'clock, and then really starts to go down after sunset. So this kind of proves you need that warm rising air. You want the air to heat up throughout the day. Remember, the max temperature in the summer is often 3, 4 o'clock. So really right around and then just after that max heating of the day, you have your best air mass in place for thunderstorms to develop. And especially if there's, say, a cold front coming through, that extra lifting mechanism, you have that sort of extra oomph to get your thunderstorms forming and then strong enough to be considered severe. That's sort of the temporal distribution. We look at the seasonal distribution, and we'll find that, again, probably unsurprisingly, you'll note thunderstorms peak from May through about August. So again, the graphic shows the month and then the number of these different types of severe storms. And we noticed, right, as soon as you hit May, the number of storms starts to increase pretty steadily. We have an initial peak here around late May, early June, around Memorial Day or so. A bit of a lull, and then it sort of goes back up again, and we sort of have a consistent secondary peak here from later June through most of July. And then come August, it actually starts to decrease a little bit. By sort of that second half of the summer, any sort of semblance of cold air has really, really pushed far, far north, far away from Long Island. So as you get towards the later part of the summer, you start losing that air mass flashing. You generally don't have quite as many of those strong cold fronts, the cold air pushing the warm air out of the way. So you generally start to see a decrease in the severe weather the second half of the summer, but it can still occur. So again, really the peak is late spring and especially the first 2/3 of summer or so. Then notice it's hard to detect, but there can sometimes be these very, very minimal secondary peaks weeks of storms in October and November. And that's sort of the opposite of spring. Now you have the cold air starting to come back, but there can still sometimes be a little bit of warm air left over from the summer. So occasionally you can get some frisky things happening in the atmosphere during the fall. So you probably notice that usually in October, November, there's usually at least 1 or 2 rounds of storms. And again, that's sort of the end of the warm air for the warm season. And then we transition into winter where there's very little in the way of thunderstorms. But it's not impossible really any time of the year to get a storm, just very rare during the winter months, as you can see. Then finally, just a quick look at the geography of all this. And on here, these are severe weather reports during this 27-year period. The blue dots are severe winds, so winds at least 58 miles per hour. The green dots, and again, I apologize, they're not the best graphics, they're a bit old. Green dots are hail reports, and then the red lines, those are tornado tracks during this period. So you'll notice a few interesting things probably. One is there are no tornadoes over Long Island during this time period. That's not to say you can't get tornadoes over Long Island, but they're very, very rare, fortunately for Long Island. Also, you probably notice the density of those blue and green dots seems to be higher further inland and then lower over Long Island, especially as you get towards Suffolk County in the East End. And this is not a fluke. As it turns out, Long Island is a bit protected from getting the worst of thunderstorms typically. That's because during the summer, and you can just think about previous experience, during the summer, the ocean water stays much cooler than the atmosphere. Think about the warmest ocean temperatures off Long Island, maybe what, low 70s in the summer. Meanwhile, the atmosphere, the air temperature can get up in the 80s and 90s. So as it turns out, the ocean staying cooler helps to sort of insulate Long Island a bit, essentially leads to more stable air mass or cooler air that can't rise quite as easily. So thunderstorms often, not all the time, but often weaken as they get towards Long Island because of that, what we call a cool and more stable marine layer, or layer of cooler air formed over the cooler ocean water that surrounds Long Island, both the Atlantic Ocean to the south and the Long Island Sound to the north. So you'll notice much more in the way of severe weather reports just inland in Jersey, and then it sort of decreases west to east as you go across Long Island. So storms often weaken. Maybe you've noticed this before. There's a big line of storms coming on the weather radar, and then it kind of comes through but fizzles out. And that's not just a coincidence. That is a climatologically significant signature. Again, it's the idea that this cooler ocean water helps to protect Long Island to an extent from the worst of the storms. Doesn't mean there's no storms over Long Island, but it does mean there's a slightly lower threat for severe weather, especially to go towards the eastern part of Long Island, as compared to adjacent inland areas. So an interesting quirk there for severe thunderstorm climatology. And here's a quick look at a Long Island thunderstorm. Again, not impossible to get thunderstorms. This is from about 2 years ago, May 2018. From Hofstra University, there's Hempstead Turnpike here. As I put the video in motion, sorry, it's going to be a bit laggy, probably over Zoom. And notice all the traffic going by. And notice all of a sudden you get a big gust of wind first. That's called a gust front. Sometimes precede a thunderstorm. And then we're going to get the very heavy rain, some hail, and strong winds. So pretty typical thunderstorm coming across Long Island here. And of course, you see the traffic tie up as the storm coincided with rush hour. So we see the impact certainly of severe weather over Long Island. And this idea of the gust front is just that sometimes as the air in the thunderstorm rises up, it can get very high in the atmosphere, and you end up getting some cold air at the top of thunderstorm clouds. Sometimes that cold air, now very dense and heavy, can rush down out from the edge of the thunderstorm and sort of hit the ground and then spread out, and then the air spreading out ends up being strong wind, which comes in advance of the thunderstorm. So that's a so-called gust front. So actually had a brief surge of extra heaviest wind from the storm was out ahead of it from that so-called gust front. And then a few minutes later, the main storm came in. Main part of the storm came in. I'll play it again, and you'll see a brief burst of wind here, right there. That's your gust front. And then just a little bit while later, the rain starts, and the main part of the thunderstorm with the heavy rain and wind and lightning and some small hail occurs and helps to tie up the traffic. You know, even on a good day, Hempstead Turnpike doesn't move well, and then add a thunderstorm in during rush hour, and you really have some fun. All right, so Don't see any questions popping up in the chat. So let's pop into our last topic. That's going to be tropical cyclones. And then we'll just quickly transition into the short-term weather outlook, and then we'll wrap up. So tropical cyclones, aka hurricanes, but we as scientists like to call them tropical cyclones because they're not called hurricanes everywhere. They're actually called different things in different parts of the world. Typhoons, for example, in the Western Pacific Ocean could impact Japan, sometimes China, Taiwan. And they're called cyclones off in the Southern Hemisphere, say the Indian Ocean. So they're actually called different things. So we broadly refer to these storms as tropical cyclones. It's the same thing. A typhoon is the same thing as a hurricane. It's just a regional name for it. So we call them tropical cyclones because they're storms, again, cyclones that generally form and occur in the tropics, the tropical parts of the world. So between 23.5 degrees north and south latitude. And they're just happen to be referred to as hurricanes in the Atlantic Ocean when they form there, and the Eastern Pacific Ocean. They're large, circular, rotating cyclones. And there's actually not that many tropical cyclones that form in a given year. There's usually dozens that form across the Earth. There's not that many. And that's because they need a narrow set of criteria to form and strengthen. You need very warm and deep ocean water. So warm water of at least 80 degrees Fahrenheit generally. And not only should it be warm at the surface, that warm water has to extend down to a certain depth, at least a couple hundred feet down below the surface. And that's because as hurricanes strengthen, they sort of spin up the water, sort of like swirling up a bathtub. And they can actually swirl up water from below the surface up to the surface. So if the water below the surface is cool and the hurricane spins it up, that is then going to weaken the hurricane. So hurricanes generally do bring up cooler water. So in its wake, a hurricane leaves often cooler surface temperature of the water. So if there's very cool waters below the surface, that's going to sort of weaken the hurricane before it can sort of get away from that churned up water. So warm water that also extends down below the surface. Unlike tornadoes, you actually want low wind shear for hurricanes. So tornadoes, you want wind shear, you want the wind changing with height, wind speed and direction changing with height to get things spinning around. Hurricanes actually spin independent of wind shear. They spin due to the so-called Coriolis effect, or the fact that the Earth is rotating and that its radius decreases as you go from the equator to higher latitudes. That actually causes large storm systems to spin around. So the hurricanes get their spin from Coriolis. That's why they can't form near the equator. There's no Coriolis effect there. So hurricanes get their spin from the Coriolis. Therefore, they don't need wind shear. Wind shear can actually sort of rip apart the hurricane. So again, hurricanes, you want the warm and deep ocean water. You want low wind shear or sort of a uniform profile of wind direction as you go vertically through the atmosphere. And again, you need to be away from the equator because right near the equator, you can't get a spin. That's because the Earth radius essentially stays constant right around the equator. You got the Earth sort of bulges out the equator, that's sort of the constant radius. Then the radius decreases as the Earth comes in towards the poles. Think of it as a sphere or a circle in 2D just about. So that change in radius is what gives you a spin if you travel across great distances of Earth's surface. And hurricanes are big enough to tap into that spin due to the Coriolis effect. So again, have to be away from the equator. So hurricanes generally can't like cross the equator because there's not enough spin there to keep them going. Hurricanes need that spin to sort of create an exhaust system, almost like an engine in a car. So they're called tropical cyclones for a reason. They generally form in tropical ocean waters. So you see the two maps here from July and September. Where do Atlantic hurricanes most frequently form? Notice how there's fewer in July, and we'll get into that in a couple minutes, more in September. So the blue means likely, and then green and orange, more likely places for hurricanes to form. Notice how they most generally form in the tropics, at first sort of in the Gulf of Mexico and Caribbean Sea area, and sometimes off the southeast coast of the US. This is where you have the warmest ocean water in the Atlantic Ocean generally, at least away from the equator where hurricanes can form. And this can also, and this can foster the development of hurricanes. And then as ocean waters warm up in September, we see a broader region where hurricanes can form, but again, generally most frequent in the warmer ocean water in the tropics or very close to the tropics. And you notice the arrows are the prevailing hurricane tracks. And notice how sometimes they come up along the East Coast, but generally they sort of recurve, as we say, go out to sea. That's because there's a semi-permanent feature called the Bermuda High in the middle of the Atlantic Ocean. It's often around Bermuda, hence called Bermuda High. That imparts a big clockwise spin, it's like the hands of the analog clock spinning around. So hurricanes form in the tropics and oftentimes can sort of get forced towards the Caribbean Sea in Central America and float in the Gulf of Mexico by this big high pressure, or the high pressure can sort of steer them around like a clock again up the East Coast. Generally up the East Coast and then out to sea, so they curve away from Long Island. But in rare cases, things can line up to force the hurricane in towards the Long Island of the Northeast US. Of course, Sandy is a very good example of that. Certain rare conditions all came together to help force Sandy in towards the East Coast, and eventually it hit New Jersey and gave Long Island significant impacts. So what are those significant hurricane impacts? We see storm surge and waves, sort of like a coastal winter storm, flooding, beach erosion, strong winds, straight line winds. Very rarely hurricanes can bring tornadoes and make landfall. The hurricane rain bands actually hitting land can cause, the friction of the land can cause some spinning and some weak tornadoes, but generally it's sort of the so-called straight line winds, the non-tornado winds, is what causes the big damage from hurricanes. And then heavy rain, of course, especially when they move slowly. And then infrastructure damage, of course, trees down, power lines down, roads blocked, flooding. And I bolded in storm surge and waves and heavy rain because generally when we get impacts either directly or indirectly from hurricanes along Island, it's the water that's the big influence. The storm surge and waves from the ocean water, and then the heavy rain falling from the sky for flooding, especially as you go inland, especially when the hurricane moves more slowly. So sort of two ways we get impacts from hurricanes on Long Island. So one, it is the rare case of a direct landfall, and then you can get the surge and winds and heavy rain. But two, sometimes hurricanes maybe hit Florida or the Carolinas or the Gulf Coast states even. Then they sort of come up to the Northeast, they make that recurve, and they might move slowly, and then even as they weaken, they sort of just sit and spin around the mid-Atlantic or Northeast, and that can lead to several inches of rain falling, and then you can have significant flooding. So storm surge, again, that can often be a big impact from hurricanes. So some quick bullet points on that. I know there's a lot of text on here. So storm surge ends up being worst on the so-called right side of a landfalling northern hemisphere hurricane. That is, if you imagine a hurricane hitting the eye, making landfall, think of the area to the right of the center of the hurricane, the eye. That's going to be having the worst of the storm surge generally. And that's because the winds circulate around a hurricane in a counterclockwise fashion in the northern hemisphere. So the opposite of the way the hand of the clock face would move. So that counterclockwise wind flow means that the right or east side of the hurricane is where the water is going to get pushed in by the wind from the ocean onto the land. So the water can get piled up and pushed onto shore. That's known as storm surge. That's most of the reason why you get heavy surge. It's the wind from the hurricane kicking up waves and this push of water in once the hurricane meets the shore. A small amount of surge is created by the so-called barometric effect, where the actual idea that the hurricane can have such a low pressure that there's less force pushing down on the water, so the water in the ocean can rise up a little bit. So the water level goes up a bit because of this effect. And of course, storm surge can be worse, which is sort of the dumb luck of it lining up with high tide. And unfortunately, that's what happened with Sandy. Sandy's surge was highest around high tide, and it's a big high tide at that. And that really exacerbated the amount of water coming in and led to the really devastating storm surge that I'm sure many of you remember or even experienced directly. And then finally, and this is also important along parts of Long Island's coast, bays and other sheltered locations sometimes actually have worse surge because the water in the bay is very shallow right off the bat. So then when you start piling water up on top of it, it can really get far inland, especially when you have a flat coastline along a bay, as is often the case. And as you can imagine, the South Shore of Long Island is unfortunately very prone to heavy storm surge because it's flat due to our geologic history. And that can lead to storm surge getting very far inland. And unfortunately, that was the case with Sandy, and it's happened in storms well in the past before Sandy. So some graphics here. So on the right here, this is from Bay Park, so the South Shore in Nassau County. 10.9 feet of storm surge coming in from Sandy. Again, this is an absolute worst case scenario for Long Island in terms of the surge. Hurricane took a nice hook in to the right into New Jersey. And if you sort of picture that, we were on the right side, the east side of the hurricane. And even the angle of the track of Sandy took, it forced water to straight into the South Shore of Long Island, nothing to stop it. And it coincided with a big high tide. So that led to an extra couple feet of surge that we wouldn't have had if it hit, let's say, lower tide. So 10.9 feet of surge there, totally flooded that power plant there in Bay Park. And of course, all along the Long Island coastline, even the North Shore, obviously a devastating high surge. Long Beach, as we see in the bottom left here, devastation. What ended up happening is you had the water coming in from the Atlantic side of the Barrier Island, you had water coming in from the bay side of the Barrier Island, and the water from both sides met in the middle of Long Beach. So really a bad situation there. And of course, we know New York City had significant impacts, especially lower Manhattan, parts of Brooklyn and Queens right along the water. We had, of course, flooding in the vehicular tunnels and the subway tunnels. And we know there's still some impacts on infrastructure from that, that we're still recovering from at almost 8 years later. Last but not least, tropical cycle climatology. You probably noticed those maps, more development during September, actually. So we have a peak in September. September 10th is the average annual peak of hurricane season in the Atlantic Ocean. And that pretty directly tracks ocean temperatures. Oceans, it takes more energy to heat up water than land. So as it turns out, even though our peak temperature in the land in North America is usually around late July, it can vary a bit depending on where you are and some other things, but around Long Island, usually late July is our peak heating. But the ocean is actually delayed several weeks because it takes more to heat up and cool down the ocean. So the lag in the ocean temperature takes longer to cool down in the winter. It also takes longer to warm up in the summer. So actually our peak ocean temperature is late August into early September, and therefore our hurricanes actually peak in September, early September typically. So hurricane season really starts to ramp up in August often, peaks in early September, and then can last through much of October, that peak, because ocean water is still quite warm. There's some other factors in there too that help influence this chart, but really a big driver is just those ocean temperatures. Warm ocean water is really the #1 ingredient for hurricanes, and that warmest ocean water is in early September, so that's when you have the best chances of hurricanes forming. And often sort of our significant Long Island hurricanes follow this trend. Really, it's late August through October is when we see most of our significant impacts from Long Island for hurricanes. And finally, wrapping this up, here's a look at continental US hurricane landfalls during a 68-year period, 1950 to 2017. The dots show hurricanes that hit the US, and then the colors correspond to the hurricane strength. The higher the category, the stronger the winds, so generally the stronger the hurricane. But important to note, hurricane strength is in terms of the category just based on wind. There's other aspects of the hurricane that can make it stronger or weaker. This just looks at wind, which is very important, obviously, but not the only thing. Sandy, for example, making landfall in New Jersey, is only category 1, but it's very large and very low pressure. So the storm surge is more on par with maybe a category 3 hurricane. So hence it had very, very devastating impacts for Long Island and other parts of the Northeast US. You'll note, of course, the highest density of these dots, and then especially the higher categories, is over the Southeast US, basically from the Outer Banks of North Carolina all the way around Florida towards the Gulf Coast states. But notice we do have this little secondary peak here in the Northeast. And one of the reasons is this geography. Notice how the Northeast starts to stick out. Long Island and New England sort of sticks out in the ocean. So those recurving hurricanes can sometimes clip Long Island or even make landfall. So we see this quartet of hurricanes that made landfall on Long Island during this period. So 68-year period for hurricanes that averages out to about 1 per 17 years. Of course, hurricanes are so extreme and uncommon for Long Island. There's not necessarily a rhyme or reason. Sometimes you can get a couple in a short period of time and then go a very long time without landfalls. And that's actually sort of what's been happening now. Technically, we haven't had a direct landfall on Long Island from a hurricane since Gloria in 1985 there. Sandy hit New Jersey, but we can definitely consider Sandy to be a Long Island hurricane because it had such significant impacts. But really, between Gloria and Sandy, we didn't really have much in the way of extreme impacts from tropical cyclones on Long Island. That's a 27-year gap or a generational gap. So we can definitely have an issue in terms of people not necessarily knowing what to do or taking warnings seriously when you go decades between significant hurricane impacts. So Sandy in 2012, most recent. Even now, it's been almost 8 years since Sandy. And then the actual landfalls, we had Gloria in 85, Bell in 76. And then before that, it was a little while. It was Carol and Donna, which kind of hit pretty close to each other. And notice a few New England hurricanes as well. And then some of these had impacts on Long Island. Bob, for example, in 1991, had some impacts on Long Island. But the good news for Long Island was Long Island's on the western side of the storm. And typically the western side of the hurricane is a bit weaker. And also with the counterclockwise flow, the western side means you have the wind going from the land towards the ocean, so you don't really have much in the way of storm surge typically. So it's better to be on the left or west side of a hurricane. When you're on the right side or east side, that can lead to the big impacts, especially the surge. And again, that's what happened to Sandy. Here's Sandy in southern Jersey making landfall. Long Island is right on that right quadrant, east side of the hurricane. And that, with the counterclockwise flow, can pile up the water and lead to the extreme surge. And one more thing to mention on here, the red, there's only a few of those. Those are the Category 5, the strongest hurricanes that have made landfall across the continental United States. And there's only a few of those. Andrew in 1992 devastated Miami. Camille in 1969 devastated Mississippi. And it was actually upgraded, so it doesn't show up here yet, but Michael in 2017 considered a Category 5 in the Florida Panhandle. So those are very rare, period. And then it's even more uncommon that a Category 5 hits the US. You don't even need a Category 5 to have significant impacts. Any hurricane can be significant, especially if it's large and moves slowly and brings rain and all sorts of different things. All right, so I want to just really quickly touch on the misty distant future here. I know we're starting to run a bit long, so let's do a couple seconds here and then open up to any questions or discussion. So what's going to happen here in terms of the weather forecast? Well, short term, you probably realize we're in a fairly active and dynamic weather pattern. So we've had these storms coming in, lots of wind, some bouts of heavy precipitation, and chilly. The Climate Prediction Center puts out short-term outlooks. For the next 8 to 14 days, it's saying generally cool, this blue blob over the northeast US, below normal temperatures, and generally wet, the green, the A, above normal precipitation. So it looks like maybe a bit of a lull here, but then more transitioning back towards the wetter and cooler is our best guess. And then maybe after that, as we head towards May, maybe we do get a bit of a break and finally get to some warmer conditions. Not at all uncommon, of course, for April to be a dynamic month and a wet month. Longer term for the summer, hard to guess. Summers can really be just sort of depend on some random variability, really. One thing we look at is so-called El Nino and La Nina. That's warming and cooling in the equatorial Pacific Ocean. So actually a bit far away, but this is such a big impact. You may have heard of it before. It can actually influence weather around the globe. Turns out there's no El Nino, maybe a very weak La Nina. Sometimes La Nina summers can lead to warmer conditions in the northeast US. That's a pretty tenuous connection. It's really hard to have too much insight to the summer for us here on Long Island. But one important impact of La Nina or lack of El Nino is it actually leads to a more active North Atlantic hurricane season often. So one important thing to note, and we just talked about hurricanes, is the fact that our first sort of guess at the hurricane season for the North Atlantic Ocean, Colorado State University, they're landlocked, but actually one of the leading authorities in hurricane seasonal prediction. And you'll note they're predicting a above average hurricane season. And a big reason why is the lack of El Nino. Something to watch is we might have an active hurricane season. And it's not necessarily hard and fast rule, but if you have more hurricanes, right, probably a better chance one of those or more hits the US, and maybe we could even see some impacts on Long Island. So more active hurricane season, no need to panic, but this is something to definitely consider. More hurricanes bopping around, better chance of a landfall potentially, or of a significant impact from one. And last but not least, just a quick plug for my own research. We research weather warning communication using a novel technology. We look at things like virtual reality and immersive video games to show what it looks like to be in a hurricane. And also we've developed a video game where you go into a rip current and see what you need to do. And we're going to look at flooding and some other severe weather impacts as well. Go into schools to show the VR and talk about these things. So in times of non-social distancing, certainly happy to go and do that for schools and civic organizations. So we bring around virtual reality and you actually see what it's like to be in a hurricane on Long Island without physically being there, which is nice. All right, here's my contact info, email, Twitter, and just a quick look at the sources for some of these graphics here. I've talked more than enough, I'm sure. I'm happy to take any questions. We still have plenty of time to hang out, talk, and discuss. So we'll start with the chat boxes, and then also feel free to unmute and ask any questions. Let's just see some questions first. So yeah, I see a question on a microburst. Sorry, that's a little while ago. So a microburst or a downburst, similar sort of thing. And again, a big influence here can be the idea that we have warm air rising up to create these towering thunderstorm clouds. As air rises, it's going to cool down typically. So sometimes you end up getting a pool of cold air at the top of a thunderstorm cloud, and that rising air actually sort of, rising warm air counterintuitively can lead to the air getting even cooler at the top of the storm cloud. So we call that the cold air is heavy and dense. So sometimes that cold air from the top of the storm cloud, it finally just gets so heavy, it just sinks down, rapidly sinks down. So you have this push of cold air, like this whoosh of cold air that comes down from the storm cloud, then it hits the ground, and it can't go into the ground, so it hits the ground and spreads out. And then that air spreading out from radiating away from the thunderstorm, that's essentially your microburst or downburst. It can be this quick push of very strong winds, really born out of the cold air that can be developed in a storm cloud. And yeah, and this can come without warning and can come very quickly and be brief, but again, just that brief push of maybe a 60 or 70 mile per hour wind gust can be enough to cause damage. And often just a very strong, or very narrow, strong stream of air, hence the term microburst is used. It might only be a very small area that gets hit by it, but a place that does get hit by it can have severe damage. Also a great explanation of that in the chat box from Josh Timlin, who's an amazing follow on Twitter, by the way, covering Long Island weather and climate. There can be some other impacts on Atlantic hurricane formation. We have what are called oscillations in the atmosphere and in the ocean water. So sort of patterns that can yo-yo back and forth on a period of weeks to months. So El Nino, La Nina is an example of that. And we also have something called the MGO, the Manin-Julian Oscillation. This is a pattern over, and there's a question there about the MGO in the text box. And that's just sort of a packet of extra energy and thunderstorms in the atmosphere that oscillates around, essentially. And then when that packet is in certain areas, in certain alignment, that can lead to enhanced storm activity in different locations. So yeah, certain MJO patterns can foster more in the way of Atlantic hurricane activity. And again, this is like this is something that can oscillate for a few weeks at a time. So you might have a few weeks of more active hurricanes in the Atlantic Ocean. And you can maybe have a little bit of a forecast a few weeks in advance. You can say, okay, it looks like there's going to be an active period. Teleconnections like the so-called MJO, this Manin-Julian oscillation, help with forecasting. What other geographic features apart from marine can influence Long Island weather? Yeah, so the geographic features of Long Island can have an important impact on snowfall distribution. We actually see climatologically a very slight increase in snowfall generally along the North Shore of Long Island. And yeah, that's because it's just a tiny bit colder. Generally, as you go higher in elevation, you get a touch colder. Usually you want really big mountains to see a big change in temperature, but the North Shore of Long Island, a little bit hillier, maybe even just a degree colder, but sometimes that can make the difference between snow or sleet in a winter storm. So yeah, we see just enough of the signature there where the North Shore is often just a little bit snowier than the South Shore and the East End. Yeah, it's a little bit higher up in elevation. Differences in spaghetti model. Okay, so so weather forecast models are simulation of what's going to happen in the atmosphere. It's not to be taken as 100% accurate, but it gives us a sense of what's going to happen. So essentially, a weather forecast model is run on, say, a supercomputer. You put in all the current conditions that you have going on in the atmosphere, and then say, okay, based on those current conditions, what we know about the physics of the atmosphere, let's run a computer simulation, say what's going to happen going out, say, a day or 2 days or a week, or some of them go out even 2 weeks. And the problem is with weather forecast models is they're imperfect for a few different reasons. One is because we can't measure every square inch of the atmosphere. So they're coming in with incomplete information. They don't have a perfect representation of what the atmosphere looks like. It's close, but not 100% perfect. So one, each model takes in slightly different initial conditions, as we call it. And then two, we still have an incomplete understanding of how the atmosphere works exactly. So then some of those formulas are a little bit different between each weather model. Essentially, there's different weather models, therefore, that give you slightly different results. Some of them also maybe only run for certain geographic areas, but they want to run at what's called different resolutions, or different pixel or box sizes of where each value is valid. Better resolution generally means better result, as you might expect. So for example, we have different models run by different large governmental organizations. So for example, the US government runs the so-called GFS model, Global Forecast System. Then there's a consortium of European countries that run the so-called European model. So the European and GFS models, they have their own slightly different formulas and different conditions they use and different resolutions. So they come out with different results. Turns out that often, not always, the European model is a bit more accurate than the US model, but sometimes it can be less accurate. So yeah, they're different because of those reasons I just mentioned. And then there's different ways to visualize the model, what the model is saying. One thing is called deterministic, that just saying, here's exactly what we think is going to happen. Like, here's exactly where this low pressure storm is going to be. Here's the exact temperature we think is going to happen. But as you can imagine, that's sort of fraught with difficulty because the models have uncertainty inherent in them. So we try to represent the fact that there's uncertainty with the models. Instead of saying this is exactly what's going to happen, let's give a range. The idea of, instead of saying, okay, it's going to be exactly 68 degrees at 3 p.m., say, oh, it's going to be 65 to 70 degrees. Or instead of saying there's going to be 3.6 inches of snow, there's going to be 2 to 5 inches of snow. So the reason why we use ranges is because it's uncertain. And then one way we visualize uncertainty from models is so-called spaghetti plots. Spaghetti plots show, like, say, a circle of where the low pressure center is going to be, but then it looks at several different perturbations of the model, like we use slightly different initial conditions or slightly different formulas. So then each run of the model, each perturbation shows a slightly different result. So then you show these different circles of where, like, the low pressure storm will be, and it looks sort of like spaghetti coming out, hence the idea of spaghetti models. So yeah, especially as you go further out, think about the models have slightly different starting conditions, these different perturbations. So as you go further out, they often diverge more and more. So the spaghetti plot looks more and more like spaghetti as you go further out. So one case is, yeah, the further out the prediction is, the more uncertainty there is, the more variability. And then two, if it's just a very complex situation, even just a slight change in the initial conditions or the formulas you use to simulate the atmosphere has a very big effect. So that can be why, even in the short term, sometimes the spaghetti plot is, well, very busy. Okay, what are the thoughts about next winter? Yeah, so yeah, hard to say at this point necessarily, since it's just getting out of the last winter. But yeah, usually winters go back and forth. So yeah, certainly we could be due for a snowier one again. There's really often not much to say, like, oh, this past winter was warm, so it's definitely warm again. It's pretty random. So yeah, the logic would dictate it's almost a sure bet this next winter will be colder and snowier, just because this past one was so mild and lacked snow. So yeah, we'd expect next winter will be colder and snowier. To what extent? Well, we can start taking some guesses, like come October, September, October. Though you'll note most of the guesses for this past winter in September, October said, oh, it should be pretty snowy. And on the colder side, that didn't happen. So we have a little bit of skill in trying to predict the winter, but not too much. But one thing that we've noticed is generally we've been in a pretty snowy period here this past couple of decades, like since 2000. We've generally had some good snowy winters on Long Island. Part of that can maybe be attributed to the fact the Atlantic Ocean has been warm. So it's a bit counterintuitive, but the North Atlantic being warm can actually lead to more snow. One reason can be, as I mentioned, the clashing of the air masses, the clashing of that warm Gulf Stream water and air with the cold polar air coming down can spin up these coastal storms and lead to potentially more snow. So yeah, we've been in a slightly snowier pattern here over the last several years. So yeah, maybe a snowy winter coming up again next winter, certainly conceivable. And you had to stay tuned, and by the fall, we can start taking some guesses at least. Any other questions? Feel free to pop something into the chat box. Otherwise, again, I'm at WXJase, so at WXJASE on Twitter. I try to tweet somewhat on Long Island weather and climate or other interesting things going on there. And my name, jase.e.bernhardt at hofstra.edu is the email if you'd like to reach out. Really want to thank everyone for joining and for the great questions. It's a lot of fun for me. I actually have another one of these sessions coming up in a few weeks on climate change on Long Island. So feel free to join in for that and watch out for that and really all these great events. There's several interesting lectures every week through the Hofstra Cultural Center. So really feel free to check it out. And it seems like everyone enjoyed this, so really glad to see that. Hopefully you know a bit more about weather on Long Island and can continue to remain prepared whenever you do hear a warning for a storm. So thanks so much, everyone. Again, feel free to reach out on social or email for more questions. And take care and try to withstand this cool and active pattern that we're going to be in for the time being. All right, take it easy.